I actually have a question. It's just for when we're doing like the universal sets.
Uh-huh.
When we're writing fee, I kept putting it inside the curly brackets, but then it kept like submitting it as incorrect.
Right, because the P by itself represents empty set. It is a set. So you don't put curly bracket around.
Okay.
So you have homework 9 that's due Monday, and a practice test on WebAssign is due Wednesday, just before the test. The written test, the written practice test, you're supposed to do it before Monday and bring up questions for discussion. So Monday, I can take questions on both, on the WebAssign practice test and on the paper practice test. So bring your questions, and again, I strongly advise you to do the paper one first and have your questions answered, and then do the practice test on the WebAssign. That way you will be doing better on the WebAssign practice test. All right, if there's no question on the homework, I will move on. Okay. Quit that one. Okay, there is our worksheet, and we left off right here doing these problems, exercise 6 and 7. 1 second, someone just came in. So in the problems, the application type problems, you had to first determine whether it is a combination or permutation problem, and then apply the formula. We learned the formula for combination. One other thing is the permutation problems can be also handled by the box method, because permutation means counting rearrangements. So the box method counts rearrangements. So therefore, you can use either method. But when it comes to combination, the formula is the only way to simplify. So you first identify whether it's a combination or permutation, and identify the numbers that go in, and then you apply a formula if it is combination. Um, and for the permutation also, you have a formula, so you have a choice, formula or the box method. So we did exercise 7 and 8 in the last class. So we may have done 9, but I'm going to begin with 9. A class of 12 students, from a class of 12 students, a debate team of 5 students need to be formed. Now, first you need to decide whether we are selecting and rearranging or just selecting. If you're just selecting a group of things, then that's combination. If you're counting how many selections are there, then it's combination. If you're counting how many ways are there to select and rearrange, then it's permutation. So based on the context, whether it's a rearrangements that we are counting, or just grouping, or number of ways of taking groups of things, that's what you need to determine, by reading the problem. So in this problem, it says from a class of 12, a debate team of 5 students need to be formed. So these 5 students that we are taking will be a debate team. So are we counting rearrangements? Are rearrangements different debate teams? No. When you debate team would be just a group of 5 people. Rearrangements are not different debate teams. That's why this is combination. So once you determine that it's a combination, you just have to go ahead and write down the numbers first. So it is a combination C parentheses 12. From 12, we are selecting 5, a group of 5. So C 12, 5. Once you write that, you can now apply the formula. The formula says the numerator will be 12 factorial. Denominator will have two things. One of them is 5 factorial, and the other one is 12 minus 5 factorial. Let me write the first 12 minus factorial first. 12 minus 5 factorial is 7 factorial times 5 factorial. To simplify, you should take the larger number in the denominator combined with the numerator and simplify that part first. And that will simplify to 12 times 11, 10, 9, 8. And then 5 factorial is still there in the denominator. So 5 times 4 times 3 times 2. And then if you multiply numerator numbers, all the numbers in the numerator in the calculator, and multiply the denominator numbers in the calculator, divide them, that will be correct. But it'll be easier if you just cancel common things. 5 times 2 is 10, cancels with that. 4 divides the 8 into 2, and 3 divides the 9 into 3. So we have 12 times 11 times 3 times 2. That's all you need to multiply by. And that'll be your answer. Going to, okay, that was 8, problem 8. And going to problem 9 now. Second, someone came in. Software. Number 9 says a class of 12 is planning a music show of having 5 students singing solo. 5 students are going to go on the stage and sing solo. So the question here is how many such shows are possible? So you have to think about whether order matters or not. So are we counting rearrangements or just groups? 5 students are going to be selected, and then they're going to go on the stage and sing solo. So that means these 5 students are going to the stage in an order. They're not going to the stage as a group and performing together. If they're performing together, then it's just combination. We're not putting them in any order. But they're going to sing solo means they're going to go one at a time, which means there's an order going on. So who goes first, who goes second matters. The show will be different. That's why this is permutation, because the rearrangements of the 5 students will be counted as different shows. So therefore, this is permutation of 12. Is that 12? Yes. 12 comma 5. And since this is permutation, the formula is factorial 12 divided by factorial 12 minus 5, factorial 7. And then you simplify that to get the answer. Now, by the way, I need to mention something about what to do in the test. For problems like this, first you're determining whether it's a combination or not, and then you're writing this down, and then you simplify to get the answer. So just identifying the problem as a combination and identifying these numbers correctly, that itself is worth half the credit. Simplifying and getting the number right is worth another half of the credit. So, but in the WebDesign test, you can only enter the answer. You cannot enter anything else. So therefore, I want to give you partial credit whenever you get this part right. If you get this part right, in some problems you get half credit. In some problems you're going to get more than half credit. So to get that partial credit, here is what I suggest. In the test, there will be work area for each question. You may have seen that in your homework also, but you were not required to show the work, so you didn't bother to do anything. But in the test, I recommend not showing all the work. All this work that you're doing on the paper is too much to type on the WebDesign. So what I want you to type in the work area is just this part, C12.5. If you just put that in there, even if your answer is wrong, you get half credit or more than half credit. So for each problem, each word problem like this, I want you to type type your conclusion as to whether it's permutation or combination with the numbers in it. Then I will be worth partial credit. Now here's a very common answer students write in the work area that is wrong. Something like 12,5 in parentheses with no P or C in front of it. I don't know why they write that, but that's wrong. That doesn't give you any credit. I need to know whether you identified it as a permutation or combination. So you have to put that P or C in front of it to get credit. All right. So in the work area, show that. Also, yeah, the same thing is true. I was going to mention all this in the discussion time, which is Monday. For the application of system of equations that we did, that was our first topic. System of equations and then application, the word problems. In those problems also, you need to first write down the equations, two equations, and then solve them. So in the work area, you need to write the equation so that in case your solution is wrong, WebAssign is going to give you no credit, but I will give you partial credit, or most of the time it's half credit or more than half credit for writing the equations correctly. So if you put that in the work area, it'll be worth half credit. So I will mention that again when we are doing the discussion, which is Monday. All right, moving on. Going to problem 12. No, 10, sorry. 10, from flags of 12 countries, 5 of them need to be hung in front of the UN building. So they're going to hang 5 country flags in front of the UN building. So how many ways are there to do that is the question. Is this permutation or combination? Anyone?
Permutation.
Permutation, exactly. Because you are arranging, you're placing these in front of the UN building means you're going to have to arrange them. So there is an order, so order matters. And therefore it's permutation 12.5. And then you know how to simplify. So we'll just work on identifying them. You know how to simplify. You have already done that in your homework. Going on to problem 11. Let me clear the board. Problem 11 says there are 6 faculty members. A committee of 4 is to be formed. So how many ways are there? First part is if there are no restrictions. So you can take any 4 faculty members for the committee. So first you need to identify whether it's a permutation or combination. Can anybody tell me what it is?
A combination.
It's a combination. Excellent. Because a committee means the arrangements are not different committee. I mean, committee is just a group of people together, no order there. So different arrangements of those people will not be different committee. So that's why it's combination. So part A, you're choosing 4 from the 6. There are no restrictions. So that means combination of 6, 4. And simplify that, you'll get the answer. Part B says, if Jenny and Mike must be in it, then how many ways are there? Can somebody, still is a combination, but the numbers are going to be different. Okay, it's a combination of what, what. Anybody see that? Indirectly, it means Jenny and Mike are part of the 6 faculty members, and these 2 people must be in the committee, but committee will have 4 people altogether. So what are the numbers?
I think it's gonna be 6,2.
Okay, one student says 6,2. Anyone else?
Is it 6,2 times 6,4 or not?
No, there's no multiplication. It's just a simple question of, one. There's not going to be only one thing, combination of something. All right, I will explain. There are 6 faculty members, which includes Jenny and Mike. And Jenny and Mike must be in the committee. Then how many ways are there to make the committee? Well, if they have to be in the committee, you have to put them in there. So Jenny and Mike are now in.
6.
Say again?
Would it be combination 6, 6?
No, we are not selecting 6 people. We are only selecting 4 people. And in this second part,
Is it 4, 2?
all right, so yeah, somebody said that. Jara, yes. 4-2 is correct. Very good. Because even though there are 6 faculty members, Jenny and Mike are part of the 6. Now you're placing those 2 in the committee. So after you place them in the committee, there are only 4 faculty members left. And from those 4, you're only selecting 2. Everybody said, get that?
So are we subtracting the 2 from 6
From the
faculty
6,
members?
yes, because those 2 have to be in the committee means you put them in the committee. There are only 4 people left, and you need to select 2 more from the 4. So 11B is combination of 4, 2. Jenny and Mike must be in it, means you had to put them in there. So the only way to make the committee is different is by choosing other 2 people from the 4 in different ways. There are different ways to choose those 2 people. And so,
Okay.
so this
How
is how,
would we solve it?
I'm sorry?
How do we solve it? Like complete it?
Yeah, you simplify this C42 now, applying the formula. Factorial 4 over factorial 2 times factorial 2. Okay. And so to simplify that further, you would combine one of the factorial with one of the factorial in the denominator. Normally you choose a larger one, but right now we have both of them same. So that 4 factorial over 2 factorial will simplify to 4 times 3. And then there's another 2 factorial, which is 2 times 1. So simplify the 2 and 4. Now you have 2 times 3, which is 6. So there are only 6 ways to make the committee. That's a final answer. All right.
Okay. I have a question for the first one.
Yeah, go ahead.
B15 for the first one.
You mean part 11A?
Yes.
11A. C64 is the number. I didn't simplify. You want me to simplify that?
Yeah, I just want to make sure I did it correct.
Okay. Part A is C64 because there are 6 faculty members available. 4 needs to be selected. So C64. And applying the formula, the numerator is factorial 6. And denominator will be 6 minus 4 factorial, which is 2 factorial, times 4 factorial. The formula is C and R equal to factorial n over factorial n minus R times factorial R. And that's what I'm applying. So 6 factorial over 6 minus 4 is 2. So 2 factorial times 4 factorial. Now to simplify further, I combine these 2. That gives me 6 times 5. And then factorial 2 is just a 2. And simplifying 2 and 6, you get 3 times 5, which is 15. So 15 ways to make the committee. Going on to number 12.
So I still got 15, but I did it the other way by going 6 factorial to 2 instead of doing it 6 to 4.
Instead of doing C6, okay. C6, that came out right by coincidence. Let me explain why they were right. The C64 and C62 are equal numbers, but C62 is wrong, okay?
Okay.
Good. Let me explain why they came out right. CN62 and C64 are going to come out the same. And let me show you why. Factorial 6 over 6 minus 2 is 4 factorial times 2 factorial, right? In the case of 6 minus 4, factorial 6 over 6 minus 4 is 2 factorial times 4 factorial. See that they are same?
Yes.
Right. So that's because of the factorial n minus r and the factorial r in the denominator, they are same. In other words, here's a property that we never discussed. CNR and Cn comma n minus r are equal. This is a fact that I didn't go over that. There's no reason to. But that's what happens. You know, C62, 6,4, the 4 is same as 6 minus 2. So when this second number is same as 6 minus 2, you're going to have both of them simplifying to the same. You know, so by coincidence, it turned out to be right. So if you enter that in the WebAssign, it'll mark you right, but don't count on getting it right with the wrong method. You know, if the answer is if the answer is supposed to be C, let's say 8 comma 2, and you consider the answer as 8 comma 3, they're not equal, right? So you really have to come up with the right numbers to get the answer right. So it was because of this fact, they came out to be equal.
Okay. Thank you.
Mhm. All right, so Jacob is a vocalist. He needs to sing 7 songs in a recital. He has 12 to choose from. How many ways are there for him to choose? Now here, this is not the question of how many different recitals are there. The question says how many ways are there to choose. So is it permutation or combination?
Combination.
Combination. Because the question is how many ways are there to choose, they're only asking you to determine how many different ways are there to choose them. And then if he is going to actually sing them on the stage, and if they ask you how many different recitals are there, then it'll be permutation, because now the order of the songs matter. If he sings certain song first and certain other song second, reversing them will be a different recital. So for the recital, the order matters. But when they say how many ways are there to choose, that's combination. So problem 12 is combination of 12 comma 7. Okay, moving on to 13. Before doing 13, I'm going to do a slightly different problem. I think we did that before, but I want to remind you of that. So if I say there are 5 math books and 4 computer books, and I need to arrange 3 math books followed by 2 computer books, then because I only have 5 spaces available on the shelf, so 3 math book and then 2 computer book. We did this problem. How many ways are there to do this? Okay, so if you use box method, this is obviously permutation because you're arranging them. You're arranging the books. Each math books, all the math books are different, all the computer books are different, so different arrangements will be counted as different. So 3 spots for the math book and 2 spots for the computer book. So if I choose these 2 boxes for the computer book, then you can ask the question, how many ways are there to place them? So going to the first one, there are 3 math books to choose from. So 3 for the first. 3 for the first, and so after you take 1 book, there are only 2 books left. So 2 for the, I'm sorry, not 3. 5 books are available for the first. 5, 4, 3. No repetition allowed, because once you take a book, you don't have another copy of that book. Similarly, for the computer book, there will be 4 for the first, 3 for the second. And so this part is same as permutation of 5, comma 3. From the 5, you're choosing, from 5, you're choosing 3 and rearranging. So you could have done this part as permutation of 5, 3, and this part is permutation of 4, 2, and then you multiply them. Now, clearly, the product of all these is your answer. By Mat's method, you multiply them. So when you use permutation, you're using this, you're doing this part first as this, and this part separately as this. Now the product will be the answer. So if you have to combine, see here, I'm combining all the different ways of math books, arranging math books, to all the different ways of arranging computer books. So each way of doing the first part is being combined with each way of doing the second part. That's when multiplication principle applies. So you multiply number 3 here by the number 2 to get the total number of different ways. So multiplication principle applies in that case. I just wanted to bring that up so that you can understand this question better. So go to the board. So the question number 13 says 10 students and 6 faculty members are eligible. So 10 students, 6 faculty. Write down those numbers so that you are clear, with those first. Now that these are the people eligible to serve in the committee, in how many ways the committee of 5 can be formed if first question is no restriction. So no restriction means I can select any number of faculty, any number of students to go into the committee, but altogether there must be 5. So that means you can just add up the 10 students and the 6 faculty. From all 16, I need to select any 5. So for part A, it's combination, it's clearly combination because it's committee. So committee, what are the numbers? 16, comma 5.
5.
Right. From all of the 16, I can select any 5. Now, I don't need to show you how to simplify, right? Everybody is clear on that? We have done enough of the simplifying, right? We'll focus on figuring out whether combination or not, combination or permutation and things like that. So this has to be simplified by applying the formula to get the final answer. Second question says there must be 3 students and 2 faculty members. So first you figure out how many ways are there to select the 3 students. So that'll be a combination of 10, comma 3. There are 10 students, I need to select 3 students. So combination 10, 3. 2 faculty members have to be combined. So number of ways of selecting 2 faculty members from 6 will be C, 6, 2. And I need to multiply them because of the same idea I just explained. Each one of these committees, each one of these groups will be combined with each one of these groups to make the committee. So therefore, everyone here can be combined with everyone. Again, if there are 3 paths to go from one place to the other, and then 2 paths to go from there to another place, then each one here can be combined with both to get 2 different ones. This one combines with those 2 to get 2 different ones. So that's why it's 3 times 2. The multiplication principle applies. Each one of this 3 people committee will be combined with each one of the 2 people committee to make the 5 people committee. So therefore, the multiplication will tell you how many different ways are there. Part C says there must be at least 3 students and no restrictions on the faculty. So at least when that word comes in, at least, you should remember it means 3 or more. There must be 3 students or more. The total number of people in the committee is 5. So here are the ways to do it. 3 students, at least 3 students. So you have to start with 3 students. So I can have 3 students combined with how many faculty? 2 faculty, right? I need to have 5 altogether. So 3 students with 2 faculty will be one way. Or, because it's at least, So I can either have 3 students and 2 faculty, or what other number? Anyone?
4 students and 1 faculty.
4 students and 1 faculty, or
5 students and no faculty.
no faculty. Very good. So these are the different ways. Now, this committee is C10-3. The first one, C10-3 times C6-2 product. The second one is C6-10-4 times C6-1, 1 faculty. The third one is C5 students. So from 10 students, select 5, C10-5. Okay, now what do we do with them? If you remember, remember A union B is all x's such that x belongs to A or x belongs to B. That's the idea. That's exactly what we have. Here we have a set of different ways of forming committees. That's another set of different ways of forming committees with 4 students and 1 faculty, a collection of different ones. We only have the count here. These are counts. This is a count of how many different such committees are there. And this is a count of how many such different faculties are there. But we are actually combining all of the different committees with 3 students and 2 faculty to all of the committees with 4 students and 1 faculty. So that's union, really. You're combining those different committees. So the count of the union, count of A union B, if you remember, equal to count of A plus count of B. And what else comes after that? Anybody remembers?
Minus A intersection B.
Right, very good. Count of A intersection B. This is the formula we learned for count of sets. And so here we are having union of 2 sets, and the intersection part is empty. They are mutually exclusive because these are all 3 student, 2 faculty committees. These are all 4 student, 2 faculty, 4 student, 1 faculty committee. There is nothing common. No committee is shared by for those 2. So this part is 0. And if you remember, we discussed this. If the 2 sets are mutually exclusive, then the formula comes down to this. Count of A union B equal to count of A plus count of B. So therefore, since we are doing counts, the count of this way of making committee is what this number is. Count of all these committees is what this number is. So because of this formula, the count of the total is this plus this plus this. So you basically add them up to get the final answer. So whenever you have or, the word or in between, it corresponds to adding the counts because of this formula here. Okay, so therefore, basically you had to simplify each one of those expressions and then add them up. So it's a little bit of work, a lot more work than the previous question, but there's no other way. So I'll just simplify one part of that. C10-3 is factorial 10 over factorial 7 times factorial 3. And then C6-2 is factorial 6 over factorial 4 times factorial 2. Plus C10-4 is factorial 10 over 6 factorial 4 factorial times C6-1 is 6. I don't even need to write formula there. If you remember from last class, Cn1 is n. Because if you're selecting 1, then exactly n number of ways are there. Plus C10-5 is factorial 10 over factorial 5 times factorial 5. So that's the first step of simplifying. And you know how to proceed from there. So simplify them all, and then at the end you will be adding those numbers. That's how you do that one. So remember, if there's a word at least, that means you're going to have several expressions to add up to to add up to get the answer. Problem 14 says how many eight. If you're not following any part of it, please feel free to interrupt and ask the question. 14 says how many 8-card hands are possible from a deck of 52. So is it permutation or combination?
Permutation?
No, combination, because when you give a hand of cards to one person, if you have played cards, then you will understand what I'm talking about. You have the cards in your hand, you give first 8 cards to one person, another 8 cards to another person. So it's just a group of 8 cards going to each one. The rearrangements are not different hands. So a hand is just a group of 8 cards. So the order doesn't matter when you give 8 cards to each person playing the game. So it's combination. So 14A will be combination of 52, 8. A combination of 8. How many different ways are there? Okay, so that'll be factorial 52 over 52 minus 8 would be 44 factorial times 8 factorial. So here's a situation where you must use the technique we learned for simplifying, because 52 factorial cannot be found in any calculator. So you really have to simplify using the method we learned. 52 times 51 times 50, 49, 48, 47, 46 times 45 times 45. Stop right there. And then factorial 8 will be 8 times 7 times 6 times 5 times 4 times 3 times 2. And then you cancel common factors and continue on to simplify. Part B says how many 8-card hands are possible with 5 spades and 3 hearts. So now you have to have exactly 5 spades and 3 hearts. So to answer this question, and also to answer questions coming up in the probability theory. Probability theory, when we discuss probabilities, we are going to use simple examples to illustrate. And very common simple example is to use the cards. And so the cards come up all the time in probability theory. So I need to explain exactly what kind of cards are there, in case you don't know it. Some of you know it and others may not. So let me explain quickly, but it is coming up when we discuss probability theory in that worksheet, next worksheet, worksheet 8, which is the beginning of probability. It is fully described, as to exactly what is there in the 52 cards, how many of each kind and all that. But I'm going to just summarize here. There are 4 kinds of cards in the 52 cards, and they are spades. They're called, the names are spades, diamonds, clubs, and hearts. Those are the different kinds. The spades, the diamonds and hearts are the red color cards, because some problems will be referring to color. The others are black. And there are 13 of each. 13 cards of each, altogether 52. That's all you need right now, but more details will be coming up in the next worksheet. So the question here is, how many 8-card hands can be made with 5 spades? So 5 of those 8 cards have to be spades. And how many spades are there?
13.
13. So therefore, number of ways of choosing the 5 spades will be combination 13, 5. we're just making a hand, so order doesn't matter, and that's why it's combination. C13, 5. That's how many ways are there to select the 5 spades. Now the 3 hearts have to come from the 13 hearts. So C13, 3 ways are there to do that. The product will give you the number of ways of making the hand with 5 spades and 3 hearts. So multiply them. All right, moving to problem 15. Let me clear the board. If anybody has a question on this, feel free to ask.
So for how we did 13B, how come we just didn't divide 52 instead of actually like knowing each of the cards being 13?
Okay. Yeah, there are 13 spades, 13 diamonds, 13 clubs, 13 hearts, altogether 52. Right? 13 times 4 is 52. So in this question, there must be exactly 5 spades and 3 hearts. So we are not choosing these from entire 52 cards. We are restricted to spades and hearts only.
Okay, I get it. I'm sorry. Thank you.
Yeah, you're welcome.
Oh
So
wait, can you simplify A? I just wanna.
part A, this one?
Yes.
Okay. All right, let me erase the part B to make room. Okay, so it's the product of all those numbers in the numerator. And so let's look at common factors. 8 divides 52. No, 8 doesn't divide. So 48.
It's gonna have to be 13. If you're dividing 52 from 4, it could be 13.
4 divides it into 13, yes. So we can do that. 4 in the denominator. 4 in the denominator cancels with the 52 into 13. Okay. 8 divides the 48 into 6. And 6 divides oh, I have a 6 up here. So I can cancel.
Professor, why didn't we do 6 times 8 cancels with 48?
48, yeah, I just did that, yeah. Okay, so 5 only cancels with the 50. So 5 cancels the 50 into 10. Okay, 10 there. And then 3 will divide 46. Nope, not 46. Not 47. 51. 3 divides the 51. 3 divides 51 into 17. 17. Okay, finally there's a 2. 2 divides 46 into 23. So you have 13 times 17 times 10 times 49 times 47 times 23 times 45. So that's what you need to multiply in the calculator.
Okay, thank you.
You're welcome. Going on to number 15. 15 is a different problem, a very different problem, a very different kind of problem. This is about the codes, the 6-bit codes. You know, in computer programming, computer language, the language of the computer, all the things are coded using zeros and ones, 0, 1. So an alphabet, capital A, will be coded with something like this. There'll be exactly 8 in the actual coding of the characters inside the computer. So every time you store a data, anything, you know, even on the keyboard, when you type the character A, you're getting the code of the character A stored in the memory. So that's why this code with the 0 and 1 is important in the computer science field. So we call these zeros and ones bits. These are called bits. So in this question, it says how many 6-bit codes can be made. So in other words, if I'm arranging ones and zeros like this is a 6-bit code with ones and zeros. So you can arrange any number of ones and zeros. I mean, 6 ones and zeros in any order. So this is a different one. This is a different one. 1 0 1 1 1 0 will be another one. So if you keep going, how many different ones are there? That's the question here. How many different such codes can be made? Okay, then you have to look at the question a little more carefully. What do we have here? We have only 2 symbols allowed here, but we are making a 6-bit code with only 2 symbols, 1 and 0. So therefore, you have to repeat. We have to repeat the ones and zeros. So whenever repetition is allowed to count, so this is basically same as saying we are making code words. The code words are being made with only 2 different symbols. So therefore, repetition have to be allowed. And how many such code words can be made? Remember, we did code words with repetition. What is the only method that applies for code words with repetition?
Permutation.
With code words with repetition is not permutation. Permutations will be
Oh,
without
it's the box method.
box method, exactly. So whenever a repetition is allowed, box method is the only way. So we're going to use box method. Then the codes are going to have 6 symbols. So therefore 6 bits, 6 boxes have to be filled. And then you ask the question, how many different ways are there to fill each one? Okay, how many different ways are there for the first one? In how many different ways can I fill the first one? First
2
box.
ways.
Say again?
6.
2 ways.
2 ways. 0 or 1. We are allowed to use only 0 and 1. So therefore 2 ways are there for the first one. For the second one,
1.
why 1?
No, it's 2.
You're thinking because we have used one of the symbols in the first place, we have only 1 left. No, that's not true, because repetition is allowed here. So we are allowed to use the same 1 or 0 here. No matter whether you used a 1 or 0 in the first box, you are still allowed to use 1 or 0. Repetition is allowed. So 2. And for the next one?
2.
2.
2. All of them are going to be 2. When the repetition is allowed, that's how it happens. So it's going to be 2 to the power 6. So you need, I mean, here it's 6, so not too bad, but if the number exponent is bigger, you need the calculator with the exponent. So that's why I said you need a calculator, scientific calculator that allows exponents. 2 to the 6 is 64. So there are 64 different codes with ones and zeros. 64 of them are there. Okay, so let's go to the second part, part B. Let me clear the board, part of the board at least. Okay, so there are 64 codes allowing ones and zeros. The second part says, if there must be exactly 1 1, if you're allowed to have only 1 1 in the entire code, then how many are there is the question. How many codes are there? Okay, so I'm going to explain how to do that. Still, I'm going to apply the box method. I have 6 boxes because I'm making 6-bit code, but this time I'm only allowed to use 1 1. So the other ones will be zeros automatically. So I can ask the question this way. In how many ways can I place a 1 in these boxes? If I place the 1 in here, that's 1. That's 1 code. All of the rest will be zeros. Instead, Instead, if I place the 1 here, that's another code. I have only one to place. Instead, if I place the 1 here, that's another one. So how many do you see? How many different codes are there?
6.
6, exactly. There are 6 ways to place the 1. You can answer the question. Everybody see that there are 6 ways to place the 1. There are 6 boxes. I can place only 1. So there are 6 different ways. So there are 6 different codes with exactly 1. You can also answer that by saying there are 6 boxes here. I need to choose 1 for placing a 1. So that's same as asking in how many ways can I choose 1 box from 6 boxes? So C6, 1, combination 6, 1. I'm only choosing 1 box from 6 boxes. So C6, 1 is the answer, which is equal to 6. That's another way to calculate that. But you can already see if I place the 1 here, that's a code. If I don't put the 1 here and put the 1 here, that's another one. So there are 6 ways to place the 1. You can already see that directly. But the combination applies too. If you recognize it as a combination, it helps you solve any problem like this. So let's go to the part C. There must
I have a question though.
Sure.
So how would we know if the answer is 6 if all of them would just be empty boxes? It would just matter the count of the boxes?
No, it says how many codes are there, how many 6-bit codes are there with exactly 1. I can even write them down. So let me write them down. See, 1, and the others are 0. This is one of them. Agree with that?
Yeah.
And 0, 1, 0, 0, 0 is another one. Okay?
Okay.
0, 0, 1. So if I have only 1 to place. So if I place that 1 in the first box, I get this. If I place that 1 in the second box, I get this. If I place 1 in the third box, I get this. So how many? There are 6 ways, right? There are 6 ways to place the 1.
Yes.
Yes. So that's why there are 6 codes. The answer is 6. And you can also see that by doing this. There are 6 boxes here. I need to choose 1 box for placing the 1. So therefore, C61 is the number of ways, which is also equal to 6. That's another way to look at it. Okay, so if you understood that, then you should be able to tell me the answer for the second one, the third part. If there must be exactly 2 1s, then how many ways are there? How many codes are there? So they're going to be 6-bit codes, but you can only have 2 1s.
Wouldn't it be 64?
64. Where are you getting that from?
Because they gave us the code with just 2 1s in the beginning.
Okay, the 64 is the total number of codes that we have, allowing any number of 1s and any number of 0s. Okay, that's how we got that 64.
Okay, I get it now. So for C, we're only limited to having 2 1s when
Now we are limited to having
unlimited.
2 1s. Anybody has an answer for that, part C?
12?
Instead of, where did you get the 12 from? How did you do it?
Is it 15?
15?
Mm-hmm.
Okay, how did you get that answer? Where did you get that number from? Okay.
Is a combination of 6, 2.
Right, that's what I wanted to hear. C6, 2 is right, excellent. All right, so I wanted to see if anybody can see that. I'm glad one student was able to see that. There are 6 boxes this time, and we need to place 2 1s. So if I place the 2 1s here and here, that'll be 1 code. Instead, if I place them here and here, that's another code. So basically the question comes down to in how many ways can I choose 2 boxes from 6 boxes to place the 1. So that's why it's C6, 2. That's how many ways are there to place the 2 1s. So that's how many different codes are there with 2 1s. Everybody understand that?
Yes.
Okay, good. You need to simplify that. So factorial 6 over factorial 4 times factorial 2, which is equal to 6 times 5 over 2, 15. So there are 15 of them. I have seen students trying to write them down, actually, write all of them down because they forget how to count it. Well, it's not going to work. The 15, maybe you may be able to write them, but the 64, you won't be able to. That's way too many. So don't try to write them, just learn the technique for counting. These are all going to come up again when we do probability. We are preparing for probability theory, remember that. Feel free to ask questions if you're not following any part. I'm on problem 16 now. Problem 16 says how many, how many 7-bit codes contain 3 ones and 4 zeros? It's, I mean, this question is worded differently from the question number 15, but the question is essentially similar. So here, 7-bit codes, we are making 7-bit codes, so 7 boxes, but we are allowed to have only 3 ones. The remaining boxes will be 0. So 3 ones have to be placed in 7 boxes. So ignore the zeros. If you put 3 ones, the remaining boxes will be automatically zeros. Then how many ways are there? So can anybody answer the question?
Combination of 7, 3.
Right, exactly. So like I said, it's very similar to the previous question. It's just worded differently. So in the 7 boxes, you need to place 3 different ones, 3 ones in 3 different boxes. So basically the question comes down to how many ways are there to choose 3 boxes from 7? And this is how many are there. Okay, moving on to example 3. Example 3 is about 2 words, mad and dad, and how many different. Now, before that, let me go to a question we did before. Let's say the word is map. How many different ways, how many different code words can be made by rearranging the letters of this word? That would be same as saying it's permutation. We are rearranging them, right? So you can either use permutation or box method. Whenever problem is permutation, the box method also applies. So if you use box method, then we are making 3-letter code words using these 3 letters, MAP. So there are 3 ways to fill this. No repetition because you have only each letter only occurring once. So 3 ways to do the first, 2 ways to do the second, 1 way to do the third. Also, it can be done as permutation of 3, 3. 3 letters are given, all 3 are being rearranged. So it's permutation 3, 3, and permutation 3, 3 is factorial 3. Because if you apply the formula, the numerator is factorial 3, denominator is 3 minus 3 factorial, which is 0 factorial. 0 factorial is 1. So it's 3 factorial, which is equal to 3 times 2 times 1, which is 6. Same as this. So you can do it in either way. If the 3 letters, if there are 3 different letters. So what we are going to do next here in the example 3, we're going to learn how to figure out the number of rearrangements when the letters are matching. When the letters are matching, it's a different story. So that's why I chose this example to explain that. Example 3, if your word is mad, then clearly there are the letters are different, so we can do it the way we just did in the previous exercise. So the number of different words is 6. Permutation 3, 3, which is 6. So there are 6 words there. But if the word is dad, D-A-D, then if you calculate it this way, you will get 6, but you're not going to have 6 different words. And that's why I'm showing you all those details. So look at this worksheet. If the 2 letters are different. I used two different colors, red and green. So if you consider them as different, like red D and green D, then you have 6. See, altogether in these 3 boxes, you have altogether 6 of them. But because the D's are same, the DAD with the green D at the end or green D at the front, these are actually same words, right? These two are actually same in this first box. And second box, these two are same. And these two are same because the D's are same letters. And so how many different words do we have? 3, right? Only DAD, DDA, and ADD. Only 3 different ones are there. So the question is, how do we calculate the number of different words when there are matching letters? It's clearly a smaller number, but how do we find it? I'm going to explain that on the board now. So by looking at those 3 boxes, you can see that what are these 2 words in the first box? It's the DAD with the green in the back, the DAD with the green in the front. Basically, they are the word dad with the 2 D's swapped. If you swap the 2 D's, you're getting the second word. And here also in the second one, if you swap the 2 D's, you're getting the other word. Swap the 2 D's, you're getting the other word. In other words, it's because of the fact that when the D's are swapped, the word is not different. That's why the number of different words are now 3 instead of 6, because the 2 D's, swapping them will not give you different words. So therefore, to derive a formula for this situation, we have to understand this problem this way. The actual number of different words is 3 in this case, right? In this case, the actual number of different words, completely different words, are 3. So that 3, there are, so if the distinct number of distinct words that's what we need to calculate. Call it n. In this case, that n, number of distinct words, times the words, how many ways are there to swap the two D's? In fact, that's 2 letters can be swapped in P2 2 ways, rearranged. 2 letters can be rearranged in P2 2 ways, which is equal to factorial 2, which is equal to 2. So I'm going to write it as factorial 2. So there are 3 boxes here, right, which represent 3 different words. Those 3 different words, within each one, if you rearrange the 2 D's and consider them as different, then you get the 6, the full number 6. In other words, what I'm saying is the actual number of different words n multiplied by the number of ways of rearranging the 2 matching letters, which is factorial 2, that is what equal to 6. We got all 6 different words that are listed here by multiplying the 3, which is this is the 3, by the factorial 2. Factorial 2 is 2. 3 times 2 is 6. That's why we are getting that 6 for the entire 2 boxes. If you actually count them as different words, you're getting 6, right? That 6 comes out of the fact that 3 distinct words with each D's rearranged in factorial 2 ways means that 3 times 2 will be the total number of words. So this equation is true. And from this, if I solve for n is equal to 6 over factorial 2. What I'm trying to say is to figure out how many distinct words are there, you first figure out how many words are there if the letters are actually, the matching letters are actually different. If the 2 D's are considered to be different, then there are 6 words, right? You divide that 6 words by the number of ways of rearranging the 2 matching letters. That'll give you the 3, the actual distinct words. That's the point I'm trying to make. So what do we do to figure out the count of distinct words? You first figure out what is the count of the words, assuming the 2 matching letters are actually different. That's how you get that number first. And then you divide by the number of ways of rearranging those 2 letters that are matching. The 6/2 will give you the 3, correct number. So let's do, I have expressed all that in this worksheet, as you can see. So let me ask you a slightly different question now. If I have I'm just making up a word. Okay, so if this is the word given to you, and if they ask you how many distinct words can be made by rearranging the letters of this word, then you first find the number of words you get by assuming the 2 p's are actually different, and that'll give you factorial 3, because there are 3 things being rearranged. And so P33 is the answer, right? Permutation of 3, 3, which is factorial 3. You put that number first, and then divide by the number of ways in which you can rearrange the 2 matching letters. That's factorial 2. So therefore, 6/2 is 3, will be your answer. Okay, if you understood that, then can you tell me what the answer is for exercise 17? DREDD, that's the word.
Would it be 5 comma or P 5 comma 5?
One more time. What is that again?
P parentheses 5 comma 5, because all the letters are the same.
Yeah, if you assume that all the letters are different, then this is how many ways are there to rearrange. That's all, if all of them are different. But there are 3 Ds that are matching. So we're not going to have this many different words. We're going to have fewer words.
So would it be P 5 comma 3?
No. We are not rearranging just 3. We are rearranging all of them. That's why I explained in here, in the previous question up here, we are rearranging the 3 letters of the word dad, D-A-D. So if you assume the 2 Ds are different letters, then there are 6, as you can see. If the 2 Ds are different, that's why I'm using 2 different colors for the 2 Ds. If they're actually different, then there are 6, but they're not different. So because they are matching, the 2 words in the first box are same words. 2 words in the second box are same. 2 words in the third are same. So that's why the actual different words I have are 3. The DAD, DDA, and ADD. That's it. I have only 3. To get that number, 3, the technique is to figure out how many are there, assuming that all the letters are different. That will be 6. And then figure out how many ways are there to rearrange the 2 matching letters. That's factorial 2. So you need to divide. I just explained to you why you need to divide. 6/factorial 2 gives you the actual distinct words, 3. There are only 3 distinct words in that collection. So apply that same idea here. There are 3 matching Ds, right? So to figure out how many different words are there, you first figure out if the letters are all different, how many different words can be made. We arrange 5. If all 5 are different, then P5, 5 different ways are there, which is factorial 5.
Over factorial 3?
Over factorial 3, exactly. So therefore, the actual number of words we have is factorial 5 divided by factorial 3. The number of ways of rearranging the 3 letters is equal to factorial 3. P33 is factorial 3. So that's what you have to do. So 5 factorial over 3 factorial is same as 5 times 4. We learned that before, which is 20. So now we know there are only 20 distinct words because of the matching letters. Okay, so exercise 18. Anybody can tell me the answer?
Is this 6 factorial over 3 factorial?
6 factorial over 3 factorial. Exactly. Very good. Let me make up, I thought I have another problem, but I don't. So let me quickly make up another problem. If it is, okay, look at this one. Can anybody tell me how many distinct words can be obtained by rearranging these?
P7, 3.
No, we just went over that in the previous problem. Why do you think it's P7, 3? There are 7 letters. We are not choosing 3 and rearranging. No, we are rearranging all of them.
So it's 7, 7.
P7, 7 ways are there if all the letters are different. So that will be factorial 7. But not all the letters are not different. There are 3 P's.
Is it over factorial 3 factorial 2?
Right, exactly. So the actual number of distinct words that we will be getting is equal to factorial 7 divided by the number of letters that are matching. There are 3 P's, so number of ways of rearranging the 3 P's is factorial 3. You have to divide by that. And also there are 2 A's. So number of ways of rearranging those 2 A's had to also go in the denominator, factorial 2. So this is the answer for that. Of course, you have to simplify. So this part is equal to 7 times 6 times 5 times 4. And then factorial 2 is 2. So you multiply those to get the answer. Okay, clear the screen. I need to do one more problem. How many different, okay, there are 14 light bulbs, 3 defective, includes 3 defective. So that means not the 14 count includes the 3 bad ones. That means how many are good?
11.
11 good. So in a problem like this, always first figure out how many good and how many bad are there and write it down. Very commonly using the wrong number is the common problem. So 11 good and 3 bad ones are there. And first question is, if you are choosing a sample of 4, we are randomly selecting a sample of 4, then how many samples are there? So for the first question, basically the good ones and bad ones don't matter. They are all mixed together. So altogether there are 14, and we're just choosing randomly choosing 4. So how many ways are there to choose the 4? That's that's simply choosing any 4. First of all, is it combination or permutation?
I'm sorry, how did we get 11 good light bulbs?
Because there are 14 light bulbs that
include and 3 defective, okay.
3 bad. 14 includes 3 bad. So 14 minus 3, 11 is the good one. Okay. The number of good bulbs is 11 because the 14 bulbs include 3 bad ones. You got that, Samantha? There are 14 bulbs, which includes 3 defective bulbs. That's what it says, okay? So if I subtract the 3 from the 14, I'm getting 11 for the good bulbs. 11 must be good, right? You need to tell me whether you understand or not. Samantha.
Yes.
Okay. Now we are choosing sample. So how many sample of 4 can be made? So that for that sample, you can just go back to the 14. From the 14, I'm just choosing any 4. Is it permutation or combination?
Combination.
Combination, because we are just taking a group of 4 bulbs. We are not arranging them. No arrangement is being made here. So it's combination of 14, 4. That's the answer to the first question. Simplify that, that'll be your answer. For part B, how many sample contains all good bulbs? So if you look at the sample that we have made in the first one, if I call these good ones as G1, G2, G3, and so on, and the bad ones as B1, B2, B3, basically in this collection of samples we have, some of them will be good, some of them will be bad, like this: G1, B1, B2, B3. That's one, right? Any collection of mixture of good ones and bad ones will be there. So one of them may be just G2, G3, G5, G6, that'll be also there. And B1, B2, B3, G1. So there are all kinds of combinations will be there. The second part says, how many samples contain all good bulbs? That means we have to count these, the ones that have all G's. So there may be another one with all G's, and I need to count how many of those are there. Isn't that same as saying how many ways are there to get 4 bulbs from all of the 11 good ones, right? They all have to come from the 11 good ones. So that's how you count that. Combination. So part B answer is all of them have to be good, means all of them have to come from the 11. So C 11, 4. That's how many ways are there to get all good ones. Simplify that to get the answer. Part C, how many samples contain at least one defective bulb? Okay, so one defective means I'm getting 4 bulbs. So 3 good, 1 bad, or 2 good, 2 bad. See, at least 1 bad means 1 bad or more. So 2 good, 2 bad is another way. And 3 good, 2, 2, and 4 and 1. Okay, 3, 1, 2, 2, and 2, 3 here. Sorry, 2 good, 1 good, and 3 bad. Yeah, 3 good, 1 bad, or 2 good, 2 bad, or 1 good and 3 bad. We had to stop there because only 3 bad ones are there, right? So we can't go to 4. So that means this is C 11, 3. Good ones had to come from the 11 good ones, and then bad one have to come from the bad. So C3, 1 ways are there to get 1 bad. Plus, wherever or is, remember, plus. And then C11, 2. That's how many ways are there to get 2 good ones. 2 bad will be times C3, 2. Plus, 1 good comes out of 11 goods. So C11, 1 times C3, 3. 3 bad ones have to come from the 3 bad ones. And then you had to simplify. Some of them are fairly easy. C3, 1 is 3. C11, 1 is 11. C3, 3 is 1. We learned in the last class. So some of them simplify easily. And the others you have to compute and then simplify the whole expression to get the answer. Okay, so we are finished and we are out of time also. These additional problems here are just additional problems for your own practice. We don't have to worry about that. Okay, so we have completed our entire part 1 of the course. Now, if you have any question on what we did today, or any question on your practice test on the paper, or any question on your homework today, there is homework today on these things. And if you have any question on the practice test on the written sign, all of them will be taken in the next class. So next class is going to be pretty much all discussions, answering questions, preparing for the test, essentially. So you need to do those practice tests to have your questions ready. If you just come to the class and watch me do the problems, it's not going to help much. You cannot prepare for the test by watching someone doing problems. You have to do it yourself, and then when you cannot do it, you watch somebody else do it. It clicks better in your brain. If you just watch somebody do it, it won't click. Unfortunately, that's how brain works. If you try first, then watch how it's done, you learn much better. It actually goes to your memory much better. Just watching doesn't help. Okay, so you must do them and bring your questions. All right, that's all I have. So enjoy the rest of the day and the weekend. And next Monday is going to be discussion class. Wednesday is going to be test. All right, bye now.
Okay, thank you.
Yep, thank you.
Goodbye.
Bye-bye. If anybody has questions, stick around. Otherwise, you can leave.
I'm sorry, I'm just getting the last bit of the notes.
Okay. Yeah, no problem.
Thank you, Professor. Have a good day.
You too. Bye-bye.
By any chance, during the exam, are we not allowed to use our notes?
Yeah, you're not allowed to use notes. You have to memorize all those formulas. Nothing. You're not allowed to have anything in front of you. Only scrap papers and pen and calculator. That's it.
Okay, no problem. Is it okay if my phone is my calculator?
No, I forgot to mention. You cannot have the phone in front of you.
Okay, so it needs to be an actual calculator only.
You need an actual calculator. Phone is not allowed in front of you because you may be doing communication with the phone. You won't be able to see that, right? So phone cannot be in front of you.
Okay, no problem. Thank you. Have a good day, Professor.
You too. Bye now.